If you were to calculate the sample variance by dividing the sum of squared deviations by n, the average of all sample variances would then be what compared to the population variance? Either smaller than, equal to, larger than, or independent of. Okay, now the key here is to consider that we are looking at the idea of all sample variances, and we're going to take the average of all sample variances. Now, they're certainly not going to be independent of. The whole point of a sample variance is because you can't directly measure the population variance, and you're hoping to use what you see in the sample to estimate what's going on in the population. So you're using sample variability, the amount of variation in a sample, to try and estimate the population variability. Now think for a moment what that means. Think about a population and how much variation is possible within a population. Whether we're dealing with ages or heights or marks on a test or something like that, there's bound to be a lot of variation in a population. But regardless of the amount of variation that's actually in the population, when you are forced instead to only look at a smaller sample, the amount of variability available in the sample is very likely going to be less than what is in the entire population. So if you're looking to estimate a population by taking a sample, even though there are many different kinds of samples that could be taken from that one population, most of them will show less variability than what is possible by looking at the entire population. So on average, when you look at all of your sample variances, you're going to expect that the sample variances will show you an average that is smaller than the population variance. Samples are not able to overestimate. When you look at all of your sample variances, you're not going to be overestimating, you will be underestimating. So when we take a sample variance, and we know that something like this is going to underestimate this because it's too small, the way to take this value, which is often too small, is to artificially boost it up. Now, you can do that by subtracting 1 from the denominator. If you had a number like, let's say, 10 over 5, this gives you 2. If you decided that this is too small, one way to adjust for it would be to subtract 1 from the denominator. So 10 over 4 gives me 2.5. When you take 1 away from the bottom, it boosts the total value of the fraction. That's exactly why we take 1 away from the denominator here. We understand that samples show too little variation when trying to estimate what's going on in a population that we really want to be able to describe. So we give it this artificial boost. That's why we have the n minus 1. So the answer here is A, smaller than.